Hello everyone, welcome back to my channel. Today we are going to be looking at procedurally generated tile maps in the Godot game engine using the wave function collapse algorithm. Wave function collapse has become quite a popular method of generating maps in games like Townscraper, because creating detailed and interesting game worlds can be extremely time consuming, as a level designer might have to manually place a tile in each of the grid locations. With WFC, we can generate both 2D and 3D maps or structures in the game world using some association rules between different tiles. Today we're going to be looking at my implementation of WFC, where I'll extend Godot's TileMapLayer node into a new node, which will procedurally populate a grid. I'll be using GDExtensions to write the procedural generation logic in Rust. So let's get started. Wave function collapse, or model synthesis, is a family of constraint solving algorithms which are commonly used in procedural generation. You can take a look at the Wikipedia article here, or Maxim Gomin's original repository on GitHub. This technique takes an input bitmap and, for a given tile resolution, figures out the association rules to all neighboring tiles. Using these rules, new maps can then be generated using WFC, which follow the same association rules. Yeah, we're going to do things a little differently. We're going to code our associations ourselves. For our project, we'll be using Kenny's isometric roads asset. This asset makes use of these tiles, which are really suitable to demonstrate the power of wave function collapse. You can find these assets on Kenny's website. All right, let's begin. So let's first look at how tilemap layers usually work. So we can start a new project. Let's call this WFC TileMapLayer demo. And we don't change anything here. We have the editor open. Let's start with a 2D scene and add a child node, which would be a TileMapLayer. And let's save this scene. Yeah, that's all right. And we need to start from here. So we need to define a new tile set. And the tile set shape would be isometric. And the tile layout would be diamond down. I'll show you in a second why this is. And the tile size is 132 pixels by half of that. That's 66. And then we set the tile set. Let's come over here. And I'll copy the tile set that I've prepared for this project. What I've done here is simply taken Kenny's tiles and laid them out horizontally in one line. I've also chosen only some of the tiles because they seem to work well. And you can get a hold of this sprite sheet from the GitHub link of this project, which you'll find in the description. So the change that we need to do here is make sure that tiles are squares and they would be drawn on top of each other. So there is a bit of transparent region, and this transparent region is different for each tile. And hence the tile layout here that works in the way that we want to. Now you can go to the tile map and simply start drawing. Yeah, so let's see. This one. And right. And so on. And you could build your map this way manually. However, we are going to extend this node using GDExtensions and code up our procedural WFC logic in Rust, which will allow us to generate a map using these tiles and following the association rules. For instance, how these tiles connected to each other, but somehow this one is placed wrong, so it doesn't connect to the other tile. And the algorithm will take care of that and place tiles which only have associative relations with each other. So let's understand how this is gonna work. Let's assume we have a tile, and if we look at it in the isometric layout, we have these 4 directions: northeast, northwest, southeast, and southwest. And then there could be other tiles which have associative connections to our central tile. So if we try to name the southwest side, we can call it green, white, empty, white, green. And this connects to the northeast side of the tile which is on the southwest of our central tile. So we need to look at the opposite direction of the tile to have the same connectivity type that we have on the side that we are facing. And similarly, for the northeast tile, we need to look at that tile's southwest direction and see if they line up. And similarly for the southeast, we have a brown base and a green layer on top, and that connects well to the southeast side of our central tile, as the northwest side of that corresponding tile is the same type. And similarly for the northwest tile. Here's another set of matching tiles that we have for all the 4 directions. So let's say we enumerate our directions in the following order: southwest, southeast, northeast, and northwest. And the direction is given by a tuple. And this is essentially how the diamond down layout works. All the tiles that are indexed in the positive y direction point southwest, and all tiles that are indexed in the positive x direction point towards southeast. And then for our given tile, we can have this connection map for each of the 4 directions. This one is a different tile, and you can see that it has a different array of connection types. Here's yet another one. This one is a road tile, and hence we have the connection type of green, white, black, white, green on the 3 sides where the road can connect, and only green on the northeast side. Now let's look at how the project is set up in code. I have the Godot and the Rust folders. The Godot folder contains the Godot project and all of its assets and resources. And the GDExtension file contains links to the dynamic library. And the Rust library is called Rust here. And the GDExtension essentially calls it librust. So prefix lib is added to the package name here. If you want to understand how GDExtensions work, specifically with Rust, I recommend the Godot Rust book. Please take a look. It has all of the information that you need to set up Rust and Godot extensions for your project. In our lib.rs, we provide the implementation of the extension library for the myExtension struct and include our modules here. We can start off from the WFC map. This is a derived class of the TileMapLayer, which includes the base, a random number generator, and the WFC probability map, which I'll come to in a second. It also consists of the map size, the atlas source ID, which we read off from our tileset resource, a default tile index, which is basically a fail-safe in case we are not able to find a combination of tiles that satisfy our constraints, and a number of retry attempts that we attempt to generate the map in case it fails in the first few attempts. All right, then we have a bunch of functions. setCell is nothing but setting the cell at a particular index of the map to the tiles given by the atlas coordinates. And then we have our main function, generate new. All the functions with the func specifier are available in GDScript to be referenced directly. And what this function does is to call the internal generate WFC grid function, which I'll get to in a moment, with the given map size and retry attempts. And for each cell in the grid, we look at the internal grid representation at the given position. And I'll get to the state in a moment, but once the state is collapsed, it means that we have a corresponding tile index assigned to the current grid. And we do that. Otherwise, if the state was not collapsed, we set the cell to the default tile. And then we need to implement the base class methods for our WFC map layer class. And these are init and ready. Init is just the constructor. I'm using a default tile of just the base, which is in my sprite sheet, the 26 tile. Map size of 10 by 10. The atlas source ID is read off from the tileset resource 0 and 3 retry attempts. And the number of tiles that I'm using is 78, which you can see in the WFC tile dictionary. I just have a simple conditional here where I'm comparing the tile sets that I read from the source atlas to be equal to the number of tiles that I'm expecting. And if that's true, then I go ahead and generate a new map. And this is just the class that will be exposed in Godot. Then let's come to the tile dictionary. So number of tiles that I'm using in this project and which are in the sprite sheet are 78. Then the directions are as you saw before. And then we have this connection type enum, which lists all the connections that we have in our tiles. And then for each tile, this is the part that has to be done manually. You have to label each tile and each direction with its corresponding connection type. And this way we can use this dictionary in our WFC algorithm to lay out the tiles in a procedural manner. Now let's look at the WFC probability map file. This is the meat of the logic of the WFC algorithm. So we start off with a state enum, And what this does is for each grid cell, it maintains a state, which can be either one of a wave state or a collapse state. So the wave state holds all the possible values for a tile index, and the collapse state holds the value that it is assigned to in the grid. So essentially, once the entire grid has collapsed, we have our map. And then we have some helper functions here for state. Collapse random just picks a random value out of all the possible values in the wave state and then transforms the state into a collapse state using that value. Is collapsed just returns true if the state is collapsed, otherwise false. And the values function just returns the values held in either state as a vector. All right, then there is the probability map, which holds the map of all possible neighbors. And this is obtained from our WFC tile dictionary that we saw earlier. And essentially for each tile, we look at each of the 4 directions and check the function where a tile has the same type, it's the same connectivity type in the opposite direction. So for a direction D, we check the direction D plus 2 for the other tile, and if they match up, then that tile is added to the list of possible neighbors for I. And this goes both ways, of course. And that's how we initialize the possible neighbors map. And so each element in the grid is set to the wave state with the possibility of having all possible tile indices. All right, then there's a reset function which resets all collapse state to the wave state with all possible tile indices. Then there's the pick possibility function, which essentially returns a position in the grid where we can collapse the wave. And we pick the grid location, which has the minimum possible valid tile options. And we do that because this is likely to preserve the most number of options for the other cells. Right, and then we run through the entire grid and only check if the grid state is wave, and if the possible values are empty, obviously we can't go ahead and we return none. Otherwise, we find out the minimum number of options. And then we go through the grid indices again and filter those positions which have the length of the minimum number. And out of those possible options, we just then return a random index. That's it. And the last function is set and propagate. And what this function does is for any grid index, it first collapses it to a random value. So it transforms the wave state to a collapse state and then does a breadth first propagation of the choices that remain using the collapsed value. So we start off with a queue, and then for every index in the queue and every direction, we check for all the neighbors for that current cell. We check whether the neighbors are within bounds. And then we have the possible values for the neighbor index, and that's looking at all the possible values for values in the current grid in the given direction. And for the neighbor grid index, we look at the current possibilities and only retain those that are in the possible values nx and y vector. And so the old possibilities vector is thus modified. And if the modification is true, which means the possibilities have reduced since the collapse, we also add the neighbor cell to the queue and propagate further. Of course, if the neighbor cell is already collapsed, we don't do anything. And that's it. All collapsed is a helper function which returns true if all the cells have been collapsed. And then that's the parent function, generate WFC grid, which first resets all grid cells to the wave state. And then while all cells have not collapsed, we keep picking a random cell and then calling set and propagate on it. If we're unable to pick, then we just break and we fail and we call the same function again with one retry less. Otherwise, we return true. And that's it for the WFC algorithm. All right, this is the project that's using our Rust Godot extensions. We can select it in the scene tree by adding a node and selecting WFC_MapLayer. You see now this new node that we added in Rust appears underneath the TileMapLayer. And I've already created the scene, added the camera, and added a small script to it. And essentially that's it. If we run the project, we can see that our maps are being generated. If we increase the map size to, let's say, 15 by 20 and generate again, and now we have this larger map. So that's it for this video. If you'd like to see similar content on the channel or have any suggestions for improvements, please do let me know in the comments. Of course, like and subscribe if you'd want to support my work. And as always, thanks for watching.